we are going to talk about something that's changing the way science gets done, and the exciting part is that you can be a part of it. As members of the Riverbend Astronomy Club, we've been bringing people together under the night sky for over 15 years, and we want to share how amateur astronomers and everyday people just like us, are making real, meaningful contributions to cutting-edge research in astronomy and astrophysics. So let's get started. First, a little about who we are. The Riverbend Astronomy Club is a small community of just 26 members, students, retirees, teachers, engineers, and curious minds of all backgrounds. We have held an average of 40-plus events a year, from public star parties to community and school outreach programs. We're equipped with telescopes, CCD imaging cameras, and radio telescopes. But more importantly, we're equipped with enthusiasm. And that enthusiasm is what drives everything we do. Because you don't need a research grant to do real science. You need curiosity, a bit of time, and sometimes, just a clear night sky. So what exactly is citizen science? Simply put, it's public participation in real scientific research. Volunteers like you contribute observations, classify data, or donate computing power, and that work feeds directly into peer-reviewed discoveries. It works for three big reasons. First, the data is real. These aren't simulated exercises. Your observations go into actual research databases. Second, it operates at massive scale. A research team of 5 scientists can't monitor the entire sky simultaneously, but 10,000 volunteers can. Third, the impact is genuine. Citizen science has contributed to thousands of published papers and countless new discoveries. We are going to look at 6 specific projects that directly advance astronomy and astrophysics, and all of them are free to join. The first project is Globe at Night, and this one you could literally start doing tonight. Globe at Night is a worldwide campaign that measures light pollution, one of the biggest threats to astronomy and to ecosystems around the planet. Here's how it works. You go outside about an hour after sunset, let your eyes adjust for 10 minutes, look up at a target constellation and compare what you see to a set of star count charts. Then you submit your observation through the Globe at Night app or website. That's it. No equipment required. Your data point joins over 200,000 observations from more than 100 countries, building the most comprehensive global map of light pollution ever created. That data directly informs environmental research and public policy decisions about outdoor lighting, decisions that affect whether future generations will ever see the Milky Way from their backyards. Nearly 99% of people in the United States and Europe now live under skies too bright to see the Milky Way. Globe at Night is helping us understand just how serious that problem has become. Next up is Asteroids at Home, and this one runs while you sleep. Asteroids at Home is a distributed computing project. You install a free program called boinc on your computer, and when your machine is idle, it quietly crunches data in the background, analyzing photometric light curve measurements from telescopes worldwide to calculate the 3-dimensional shapes and spin states of asteroids. Why does that matter? Knowing an asteroid's shape and rotation tells us how solar pressure, something called the Yarkovsky effect, subtly nudges its orbit over decades. That information is critical for planetary defense. If we want to know whether an asteroid poses a threat to Earth 100 years from now, we need to understand how that drift accumulates. The project has computed shape models for roughly 25,000 asteroids, and your computer joining the network adds real processing capacity to that effort. Setup takes about 5 minutes. Install boinc, search for Asteroids at Home, and attach the project. The third project takes us into some of the most exotic physics in the universe, Einstein at Home. This project searches data from the LIGO Gravitational Wave Observatory and the Fermi Gamma Ray Space Telescope for signals from rapidly spinning neutron stars, called pulsars. Pulsars are the densest objects known to science. A teaspoon of neutron star material would weigh about 1 billion tons. They spin hundreds of times per second and emit beams of radio waves and gamma rays with the precision of a cosmic clock. Volunteers donate their CPU and GPU power through boinc to sift through enormous streams of detector data, looking for the faint continuous gravitational wave signals that a spinning neutron star would produce. Einstein at Home has already discovered more than 50 new pulsars, more than any other group working with the same datasets. These discoveries test Einstein's general relativity in environments no laboratory on Earth can replicate, and they help us understand the most extreme matter in the universe. Now let's zoom out, way out, with Milky Way at Home from Rensselaer Polytechnic Institute. This project uses volunteer computers to build highly accurate 3D models of our own Milky Way galaxy. Specifically, it analyzes stellar streams, those long trails of stars left behind when a small dwarf galaxy gets tidally shredded by the Milky Way's gravity. By modeling how those streams flow through space, scientists can map the distribution of dark matter in our galaxy's halo. Dark matter is invisible. We can't detect it directly with any telescope, but we can infer its presence from how it bends the paths of stars. And Milky Way at Home volunteers are helping build the most detailed map of that invisible scaffolding ever constructed. Think about that. Your laptop's downtime is mapping the dark matter skeleton of the galaxy we call home. That's extraordinary. This project doesn't need any computing power, just your eyes and your brain. Zooniverse is the world's largest citizen science platform, and it hosts a collection of astronomy projects, including the famous Galaxy Zoo, where volunteers classify telescope images. You look at an image, answer a few questions. Is this galaxy spiral or elliptical? Does it show signs of merging? And submit your classification. It sounds simple, but it's genuinely valuable science. Artificial intelligence is improving rapidly, but human pattern recognition still catches unusual objects that algorithms miss. And those unusual objects are often the most scientifically interesting ones. Here's a great example. A Dutch schoolteacher named Hanny van Arkel was classifying galaxies on Galaxy Zoo when she noticed something strange, a greenish cloud near a galaxy with no obvious source. That object, now called a voorwerp, Dutch for thing, turned out to be an entirely new class of astronomical object. Hanny van Arkel has her name in the scientific literature because she was paying attention. More than 500,000 people have contributed to Galaxy Zoo alone. You can start classifying right now at zooniverse.org. Our final project connects the smallest scales in nature to the largest structures in the cosmos, CERN's LHC at home. The Large Hadron Collider is the biggest machine ever built, a 27-kilometer ring buried under the France-Switzerland border, where protons are accelerated to within a fraction of the speed of light and smashed together. The particle collisions that result recreate conditions from just fractions of a second after the Big Bang. LHC at home lets volunteers contribute computing power to simulate those collisions, helping physicists model beam stability, optimize collision parameters, and analyze collision data for signs of new particles. Now you might wonder, what does particle physics have to do with astronomy? Everything. The particles and forces discovered at CERN define our cosmological models. Understanding what the universe is made of at the subatomic level tells us how it behaved in the first moments of its existence. Dark matter candidates, the matter-antimatter asymmetry that allowed galaxies to form. These are particle physics questions with universe-scale answers. LHC at home runs on the same boinc platform as Einstein at home and Milky Way at home, so if you're already set up, adding it is just a few clicks. So let's step back and look at what these 6 projects collectively represent. Together, they span the electromagnetic spectrum and beyond, from visible light observations on the ground with GLOBE at night, to radio and gamma-ray data with Einstein at home, to gravitational waves from LIGO, to high-energy particle collisions at CERN. They cover the full scale of the cosmos, from individual asteroids a few kilometers wide, to stellar streams hundreds of thousands of light-years long, to the large-scale structure of our entire galaxy. And they're all accessible. Free. Open to anyone with a phone, a web browser, or a spare computer. So how do you actually get started? There are 3 paths, depending on your preference. If you want to do something tonight, download the Globe at Night app, step outside an hour after sunset, and submit your first observation. You'll be contributing to a global dataset within the next 2 hours. If you want to donate computing power, head to boinc.berkeley.edu, download the free boinc client, and attach to any of the projects we talked about: asteroids at home, Einstein at home, Milky Way at home, or LHC at home. You set limits on how much power it uses, and then it just runs. Science happens in the background. If you want to use your eyes and judgment, visit zooniverse.org. Browse the space or physics projects. Pick one that catches your interest, and start classifying. No sign-up required to begin. All 3 paths lead to real science. Pick whichever fits your life best, and you can always do all 3. The universe is 13.8 billion years old. It is unimaginably vast, and still holds enormous mysteries. And yet, here we are, a small astronomy club in our community, with the ability to genuinely contribute to understanding it. That's not a small thing, that's remarkable. The Riverbend Astronomy Club is here to help you get started with any of these projects. We're also happy to connect you with our own observing programs and outreach events. The links for all 6 projects are in the description.